do understand if you speak slowly. And certainly if you're writing homeworks, you can write them in Portuguese as well. You don't need to write anything in English. This is just a convenience for me that I do speak English here. So let me start today by tying some loose ends from last class and starting with something that was wrong. No one caught it here. But somehow I defined a simple Lie algebra I said that a Lie algebra G is called simple if there are no non-trivial proper ideals. But there's a pathological example that satisfies this, and we don't want to call that one simple. So, and let's add this. This was missing last time. And G is not one-dimensional. So the one-dimensional abelian Lie algebra doesn't have any non-trivial proper ideal, but it's not simple. Okay, so that was kind of going out there. All right, so what are we going to do today? So we'll talk a little bit more about this general stuff on structure. Then we'll talk a little bit about groups. Then we'll take a break, and then when we come back, we'll start proving Engel's theorem. All right, so what did I want to say from last time? Oh, yes, we ended up on trying to define central extension. So, again, definition. This is just to mention something we might learn later. A short exact sequence of Lie algebras is, well, G1 to G2, G3, 0. Let's call this guy I, this guy J. Morphisms of Lie algebras such that I is injective J is surjective, and the kernel of J is equal to the image of I. So we may have situations where we can have an abelian Lie algebra here, an abelian Lie algebra here, and not an abelian Lie algebra here. And this was the first non-trivial example that I wanted to give, was this one of the Heisenberg algebra. So before doing that, notice something. So just one way of producing extensions is, say you have G1 and G2 are Lie algebras. Then the vector space, which is the direct sum of G1 and G2, is also naturally a Lie algebra. Well, the bracket is what? So the bracket of a pair AB with a pair A prime, B prime is just the pair AA prime. This is the bracket in G1 and BB prime, and this is the bracket in G2. So that satisfies all the axioms. And in particular, for example, I can just take the obvious extension of, so say now the question is, let's find extensions of K2, say, by K to 1. This is the one-dimensional abelian Lie algebra. This is a two-dimensional abelian Lie algebra. Why can I put here in the middle? Well, here I can put two things that I can think of now. One of them is just the sum K2 plus K1, which is a three-dimensional abelian Lie algebra, or I can put here the Heisenberg algebra. So the Heisenberg algebra, if you remember, how was this guy had three generators, P, Q, and H bar. Well, I can just have H bar here, and then just PQ being commutative here. So I have a two-dimensional abelian Lie algebra. I can have P and Q being commutative here. P and Q do not commute here, but H bar, well, this is a one-dimensional Lie algebra, so this one is abelian. So that's an example of two different central extensions that have the same ends. And this is called a central extension because the image of this guy is central inside of this guy. This H bar commutes with everything inside of the Heisenberg algebra. So different extensions of this form, they are characterized by some abstractions that there's a homological abstraction as to what are these possible extensions. And possibly, hopefully, by the end of the class, we'll be talking something a little bit about homologies of Lie algebras. Okay. So that's it. And now let's move on to, again, constructing examples of Lie algebras. So I said I didn't want to talk about Lie groups. And I don't want to talk about anything that is differentiable. But at least today, just one time, let me mention some algebraic versions of what Lie groups are. So usually, if you heard before, so Lie groups are manifolds. So here are my groups. And Lie algebras, well, I should say here, Lie algebras are tangent spaces to these guys. So in some way, Lie algebras are a way of linearizing these manifolds that are the groups. So there's a way of going from tangent spaces to manifolds, which is taking exponential maps. And this is what I want to avoid, because this exponential object is a transcendental object, something that is essentially non-algebraic. So let's do what we can do in algebra, which is the following. So let's start with a mock definition. I don't want to go into the theory of algebraic groups, but this would be enough for our purposes. An algebraic group should probably say linear algebraic group over F, so a field, is a collection. Let's write down finite. Of polynomials in the space of n by n matrices with coefficients in F, such that what? The following, let's define the set first. G of A is going to be the set of all matrices, let's put a name, let's say A, inside of n by n matrices with entries in A. I'll describe that, what is that in a second. Is invertible. such that A is invertible. I want this set is a group. And here A is any commutative associative unital F algebra. Okay, let's walk this through a little bit. What does this definition tell us? So the idea is the following. I have just a bunch of polynomials. The coefficients of these polynomials are guys that depend on this field, F. Whenever you give me an algebra over this F, we can construct a group. So you should think of this as saying, well, the group GLN of n by n matrices with entries where? Well, you can just define it everywhere. So n by n invertible matrices with entries on any algebra makes sense. So that's the idea of this group, that you change this algebra, you get a different group of matrices with entries in a different algebra, but it's essentially the same, and it's given just by some collection of polynomials. For those of you who know algebraic geometry, it's just I'm saying that I have an algebraic variety defined over F. It's cut out by some polynomials P alpha. And it just so happened that this algebraic variety has an algebraic structure of a group. Well, and if you base change to any algebra, you get a group defined over that algebra. But now, let's give examples of what those guys are. For example, I can just choose the collection of P alphas of polynomials to be an empty collection. There's no polynomial. That's a good collection. So now you give me an algebra, A, and this set is the set of all matrices, n by n matrices with entries in the algebra A, which are invertible. Is this collection a group? Yes, it is a group. I can just compose them by multiplication, and each guy has an inverse. So that's a group, and that group is called GLN. So the associated group is GLN. It's called GLN of F. It's defined over F. Well, there's another group inside, which is the following. I can just take the determinant. That's a well-defined polynomial in matrices. But while looking at matrices that the determinant is 0, that's a bad idea. Oops. No one's stopping me. Of course I need this. I better have the polynomials vanishing on the matrices. Otherwise, that group is always the same group. The polynomial should play a role. Polynomials P alpha. And P alpha of A is equal to 0. So I can choose this collection now, P alpha to be only one polynomial, and be just the determinant minus 1. So that's a well-defined one polynomial on the space of n by n matrices with entries in the field F. So now, whenever you give me an algebra, A, what is this group? It's the group of n by n invertible matrices with entries in A, such that the determinant of A is equal to 1. Well, that's another group you should know. This is SLN. Defined over F. Let me define you another group over in a different way. Instead of giving you the set of polynomials, let me give you what that group is going to be for any algebra A. So for any algebra A, before that, let's fix B an n by n matrix with entries in F. So now for any F, for any A, let's define O of A, depending on B, to be the set of all A's inside of GL A. That's a group, which is this group when I use the algebra A, such that A transpose times B times A is equal to B. So I claim that this is a group. It's a subgroup of GLA. All right, so let's check that this is a subgroup, at least, of GLA. Say we have one matrix A and B are matrices of this group of A. That means that we have A transpose B A is equal to B transpose B B, and this is equal to B. And now we just want to check that the product AB is still in the group. So I want to check that this, but this is just B transpose A, B, A, B. I'm just using the transpose of the product. It's just B transpose times A transpose. Now this guy is B, and therefore this guy is B. Now, how do you check that this is a, the fact that it's a subspace, that's also kind of trivial here. All right, so it is a subgroup, and this guy is, if B is, first of all, if B is non-degenerate, symmetric, then this group is called the orthogonal group. But if B is skew-symmetric and non-degenerate, this is called the symplectic group. But I haven't given you the polynomials defining this group. Actually, I urge you to try to find them. All right, so why am I wasting time in defining these groups? There's a neat way in algebra of understanding what vector fields are, what tangent spaces are, in an algebraic manner. Somehow, going from the manifold to the tangent space, I said it was a linearization process. It's sort of like taking Taylor expansion up to order 1 only. That's passing to the tangent space. But we can make sense of what Taylor expansion up to order 1 is by just choosing a particular algebra A over the field F. So suppose you have an algebraic group like that. I can choose my algebra A to be the algebra F, let's say polynomials in epsilon, mod out by the ideal generated by epsilon squared. So this is an algebra. This is an associative commutative algebra. It has one guy epsilon whose epsilon square is 0. The multiplication table here, this algebra as a vector space is just F plus epsilon F. This is as a vector space. And the multiplication table is just really trivial. It's just you write any guy like this. This is just AA prime plus epsilon BA prime plus AB prime. And the rest is epsilon square is 0. But now we have if we started with an algebraic group, in particular, we have G of A. And this guy will carry the information of the tangent space. So definition, Li of G is going to be the following. It's going to be the set of X in GLF. This is a Lie algebra GLF, such that the identity matrix plus epsilon X is in G of this A. And this is not a non-trivial construction. First of all, why this makes sense. This is the identity n by n matrix. G is an algebraic group like that. So in particular, this matrix here, this is, again, it's an n by n matrix because this is in GLN. So this sum is an n by n matrix whose entries are, well, elements of the field, like this is 1, plus epsilon elements of the field. So I can think of this as an n by n matrix which has entries in this algebra. So it looks like, well, now I can ask, are the polynomials defined in the group on that matrix 0 or not? Is that matrix invertible or not? If that's the case, then I call this matrix here an element of Lie of G. So the theorem we want to prove is that this is a Lie algebra. So theorem, this is a Lie algebra. And actually, this is a Lie subalgebra. Since certainly it is a subset of GLN. So it is a Lie subalgebra of GLN. It's not entirely trivial, actually. But anyhow, so let's prove some things. So again, let's grab an X. So let's start with the proof. But before saying so, though, we see that if we were on this G being a manifold, a Lie group, then I am expanding up to order 1 near the identity of the group. So this somehow should give you the idea that we are taking a tangent space, a tangent vectors, to the identity of the manifold. So this set of matrices are really just tangent vectors, arrows starting from the identity of the group. This is purely algebraic way of saying that. Proof that this is a Lie algebra. So X is in Lie of G. By definition, if and only if this identity plus epsilon X is in G of A. A from now on is going to be the algebra of dual numbers. But then in this algebra, let's check that this guy is an inverse. So what is this multiplication? Well, the identity times the identity plus epsilon factor in common of what? This is the identity times x, so that's x, minus x times the identity, so that's x, and then the rest is epsilon squared, which is 0. So this is an inverse for this matrix. Let's look first at the bracket. Let's check that the space is closed under the bracket inside of GLN. That's somehow the easy part. All right. So let's say we have two guys. Let's say we have X and Y are inside of the Lie algebra of G. I want to check that the bracket is still in the Lie algebra of G. This is just, again, similar to saying I have two tangent vectors. I want to check that the Lie bracket is still a tangent vector. Well, so by definition, this guy is in G. This guy is in G, but G on different spaces. So this guy is in G of F epsilon divided by epsilon square. Its inverse is also there, because this is a group. This guy is in G of F epsilon prime divided by epsilon prime square. Its inverse is also there because this is a group for any algebra. And then I can just multiply by epsilon x I plus epsilon prime x. All right, let's carry this multiplication. This is just multiplications of two groups. Now, how can I multiply them? There are elements of groups on different spaces. I can just, this multiplication doesn't make sense a priori. But the point is that there's an algebra that contains these two. I can think of the algebra F epsilon prime divided by epsilon square, the ideal generated by epsilon square, and epsilon prime square. This is a well-defined associative commutative algebra. Therefore, G of this guy is a well-defined group. And certainly, all these guys make sense as a group in here. They're matrices whose entries are in these algebras, and they're invertible and everything. All right, so now I can multiply them. So let's multiply them. All right. I hate doing these multiplications. Let's see. So this is minus epsilon x. Oops. No one is telling me that this is a y. You were laughing. You knew this. You were laughing all the time. You knew this. You know this was a y. Why didn't you tell me? That was going to give me a nice 0. All right. So this is I minus epsilon prime y, I plus epsilon x, I plus epsilon prime y. Let's expand this thing. So certainly the first order is I. It's a multiplication of the identity everywhere. At order epsilon, what do we have? So we have minus epsilon x times y times y times y everywhere. But then I have plus epsilon x times I everywhere. So that guy is going to be 0. At order epsilon prime, I have a minus epsilon prime y times the identity everywhere, but then a plus y times the identity everywhere. So that guy is also 0. The next order is epsilon epsilon prime, where I pick this xy times the identity, and then what else do we pick? And we're picking a minus yx. that right? That's epsilon, epsilon prime. Sounds right. But therefore, and then the rest is always 0. Now, it contains an epsilon square or an epsilon prime square. But that's enough, because now we see that this guy is an element of the group. And because the product is a product inside of a group. But this is an element of a following group. It lives in an algebra that is smaller. I can consider this as a one variable divided by the ideal generated by this guy being the square is 0. So this, which is the bracket inside of GLN, is still in the Lie algebra. Okay, so now we have a so we have this space which is closed under bracket. What do I need to check that I have a Lie algebra, a sub-Lie algebra? What was the definition of a sub-Lie algebra? Am I missing something to check? Or is this enough already to check that I have a sub-Lie algebra of GLN? We just check that if I have two guys, x and y, in Lie of G, their bracket is still in Lie of G. Do I need to check anything else? Come on, just a wild guess. Someone has to. I have all the time in the world. I mean, 2 hours can pass really, really slowly. Just give me a guess. Or probably it's already done. So let's work on what were the definitions of a Lie algebra then. So if I have a Lie algebra and I want to check that I have some subset that is a subalgebra, what do I need to require in that subset? It's close under bracket and I can be here forever. Someone must know the answer, or at least guess the answer. Guess wrong. Yeah, sure. Por supuesto. ¿Qué estoy haciendo mal? Probablemente estoy haciendo algo mal. ¿Queda mal? Plus x, y. Tem razón. X and y. X, y. Minus yx. That's yx. That's correct. Huh. What am I doing wrong? That's right. That's y. I'll have to check this. That's one. Não, mas... Não, pode fazer a... Não, pode fazer a multiplicação destes dois primeiro, los dos últimos no final, está tudo bom. De todas formas, la pregunta continúa. ¿Qué falta? Nadie quiere ni siquiera arriesgar. No one's going to try to guess. Okay, so if I have an algebra, a requirement, the very first definition of what an algebra was, not even a Lie algebra, is that it has to be a vector space. So it's not clear at all that I have a matrix in GLN such that these conditions satisfy. And I have Y also, that this condition is satisfied. Fine, their bracket seems to satisfy this condition again. But their sum is not clear that it's there. So we need to check that. We need to check that this condition is linear in this X. So that somehow is a condition that being a tangent vector is a linear object. And that's non-trivial. So this is the definition, so let's not erase this. And here we'll need the fact that our algebraic group was defined by polynomials. So let's continue on this side of the board, because this is the point. X is in Lie of G, if and only if this guy is in G of A. That's true. This means that this guy has to be invertible. But there was a condition on the definition of G of A. G of A was the set of n by n invertible matrices with coefficients in the algebra A, and the polynomials defining the group in these matrices should be 0. So that's a condition of being in the group. Now, since I have a group, I do know that the polynomials on the identity should be in the group. So this I know is 0, because the identity should be part of the group. Now, the good thing about this algebra of dual numbers is that I can Taylor expand linearly on these guys up to order 1, because epsilon squared is already 0. So if I do the Taylor expansion with respect to x, I'm going to have only two terms. Order 0 in epsilon or order 1 in epsilon. So let's do that. Well, we will take, what is the Taylor expansion of that equation? I have 0 is P alpha of I plus epsilon x. But this is, well, at order 0 in epsilon, P alpha of the identity, plus at order 1 in epsilon, the sum of all the derivatives of this P alpha with respect to the entries. I mean, these P alphas were polynomials in the entries of the matrix, of the n by n matrices. So let's call those guys I and j. We're summing over I and j, evaluated at the identity. Now, these are numbers. Now, they are not necessarily 0, but they're numbers. Times, well, epsilon, because it's our order 1, and xij. But the whole point here is that, well, this is 0, by what we said before. So this condition here is now a linear equation on these unknowns, on the entrances of my x. These are just numbers. So if I have one matrix X that satisfies that equation and another matrix Y that satisfies this equation, the sum is also going to satisfy this equation, because this is a linear equation in these entries. These are just numbers. So that proves that this is a subspace. So usually, actually this is a common mistake. I've seen it several times, that people check that you have somehow a subset, you check that the bracket is still inside of the bracket, and then you say, okay, this is subalgebra. And there's papers with these kind of mistakes. All right. The point is now, whenever you have an algebraic group, you can produce now this Lie algebra associated to it, which is just taking the Taylor expansion of the algebraic group with values in these dual numbers algebras. So let's see what are the Lie algebras that we already know with respect to these groups. I mean, there's a reason what their names. So first of all, the Lie algebra of GLN is GLN. Well, there was no, the proof of this is obvious. There's no P alpha. The set that defines GLN, there's no P alpha. So the only thing I need to check is that for any matrix in little GLN, I can have an inverse. But this is the thing that we just checked here. So for any matrix in little GLN, the identity plus epsilon x is in big GLN because it has an inverse, which was essentially the only condition defined in this group. So this is tautological. The Lie algebra of SLN, remember, this guy is the group defined by the polynomial. There's only one polynomial, which is the determinant minus 1. This is SLN. Let's check this. So on the one hand, we have this algebra that consists on n by n matrices, let's say x, such that their trace is 0. And on the other hand, the definition of this side is that the identity plus epsilon times that matrix should have determinant 1. Let's write it down. So we have 1 plus epsilon x1, 1. Epsilon x2, 1. Epsilon xn, 1. And here we have epsilon x1, 2. Epsilon x1n. Here 1. And on the diagonals, we have the entries of the identity. So we have epsilon n2, 2. Up to 1 plus epsilon xnn. And outside we have epsilon x2, 3, and so forth. So everything that is off the diagonal has an epsilon. Everything that is on the diagonal has a 1 plus epsilon something. That's kind of clear here. So now I need to compute the determinant. There's two things. One is that this guy has an inverse. We already checked. For any x, this has an inverse. The other thing to check is that, well, the polynomial vanished. So we need to check that the determinant of this guy is equal to 1. What gives us that condition? Well, the determinant consists of picking out of each row one entry. Some shuffling, but the point here is that if I pick any guy outside of the diagonal, I'm going to have an epsilon squared. Well, unless I pick one in the diagonal, one outside the diagonal, but that's going to be a 1, so that's not going to contribute. So the only way that I can contribute to this determinant is to have all of the guys in the diagonal. But that's going to be 1, just this product of all these guys, plus the epsilon linear term. And the epsilon linear term is, well, at each point I need to choose x1, 1, and then 1 on all of these other guys, x1, 2, x2, 2, and then 1 on all the other ones. So I get x1, 1 plus x2, 2 plus xnn. And then the rest is of order epsilon squared. So the determinant of this matrix is just 1 plus epsilon, the trace of the matrix. This is kind of a mock thing, because somehow what you may have used in calculus is that there's a relation between the exponential of the trace and the determinant of a matrix. It's just that we are tricking things up in such a way that the exponential vanishes at the first step because we already have an epsilon that squared is 0. So essentially, this is the exponential of the trace. It's just that epsilon squared is already 0. But anyhow, so the point is that this is the determinant. And if I want this guy to be 0, to be 1, then better. So this is equal to 1 if and only if the trace is equal to 0. But this was the definition of being in little SLN. So we checked that the Lie algebra of the Lie group of determinant 1 matrices is the algebra of traceless matrices. All right, so let's check. Let's check tricking because I didn't give you the polynomials for the orthogonal ones. But let's check that the Lie algebra of this group that I called OB, OBN, I think. Oh no, that's just OB was, is little OB that we defined last time. So on this side, so the statement is, recall the definition here. This definition was that it consisted of matrices A transpose B plus BA is equal to 0. Those conditions. Those were n by n matrices satisfying that condition. And here, the condition on the group was that A transpose B A, well, let's not use the same letter, that for the elements of the group, was equal to B. That was the condition. Now, if I want to look at the Lie algebra, well, then I better take I plus epsilon x, take the transpose, B, and now this G better be I plus epsilon x, and this should be B. Well, up to order, the constant order, this is just B times the identity, so that's B. Plus, up to order epsilon, we have x transpose B times the identity, plus the identity times B times x. And I want this to be B, so we better have this guy being 0, which is the condition for the Lie algebra. All right, so that shows somehow that the Lie algebra that corresponds to having orthogonal transformations on some vector space is the Lie algebra that we were calling orthogonal. Okay, let me finish and take a break in a second, but let me just make a comment, because now, from now on, we're going to move on into just trying to prove an actual theorem about the structure theory of Lie algebras. But it's geometrically easy to see what the statement of what these groups are acting on vector spaces and what their defining properties are. This GLN is, well, the group of automorphism of a given n-dimensional vector space. Any automorphism is there in this group. So it makes sense that, well, just any endomorphism of the vector space is in its Lie algebra. This Lie algebra, this Lie group, is the group of guys that have determinant 1. That means that they preserve a volume form on that vector space. And the notion of preserving that volume form in the Lie algebra is interesting because it corresponds to having trace 0. This is something like having divergence 0 for vector fields. As for the orthogonal condition, being in the orthogonal group, say this B is non-degenerate and symmetric. Just take it to be the identity, that matrix. This group is the group that preserves lengths. So it's easy to see what the group acting on the vector space is. But however, this orthogonal Lie algebra satisfies this condition. That is, if you take the transpose, if this was the identity, it's just that the transpose is equal to minus itself. Where does it come from? And it comes just by differentiating, taking the linear approximation to those Lie groups. All right, so we'll take a break, we'll come back, and then we'll prove Engel's theorem today.